Earth hazards and their mitigation. Geological events can pose hazards to human populations and infrastructure. Here are some examples. Earthquakes. These mainly occur when two tectonic plates move against each other, releasing energy that causes the ground to shake. The shaking can cause damage to buildings and infrastructure, and can trigger landslides or liquefaction, which can be further hazards. Earthquakes are recorded and measured using seismometers, which are instruments that detect and record ground vibrations caused by seismic waves. The two most commonly used scales to measure earthquakes are the Modified Mercalli Intensity Scale and the Moment Magnitude Scale. The Modified Mercalli Intensity Scale is based on the observed effects of an earthquake on people, structures, and the natural environment. It ranges from 1 to 12, with 1 being imperceptible and 12 representing complete destruction. The scale is subjective and varies depending on the location of the observer. For example, an earthquake with an intensity of 7 in a rural area may have a different impact than the same intensity earthquake in a densely populated city. The moment magnitude scale, on the other hand, measures the amount of energy released by an earthquake at its source, also known as its magnitude. The scale is logarithmic, meaning that a magnitude 6 earthquake represents 10 times the amplitude of a magnitude 5 earthquake, and 100 times that of a magnitude 4 earthquake. The scale has no upper limit, but earthquakes of a magnitude of 9 or greater are extremely rare. Both scales provide useful information about the strength and impact of an earthquake, and scientists often use them in combination to better understand the seismic activity in a region. Next, let's look at volcanic eruptions. Volcanoes release lava, ash, pyroclastic flows, which are hot gases and ash, and mud flows. These can destroy homes, vegetation, and infrastructure, and can cause respiratory problems for people and animals in the area. Volcanic eruptions can also cause climate change, as the ash and gases released into the atmosphere can block sunlight and cause cooling. The type of volcanic hazard associated with a volcano can be linked to the type of magma that the volcano erupts. Basaltic magma is relatively low in viscosity, which means it is thin and flows easily. As a result, basaltic eruptions are typically not very explosive and do not produce significant ash or pyroclastic flows. However, basaltic eruptions still pose a hazard from lava flows, which can destroy property and infrastructure in their path. Andesitic magma is more viscous than basaltic magma, which means it is thicker and flows less easily. As a result, andesitic eruptions are typically more explosive than basaltic eruptions and can produce significant ash and pyroclastic flows. During heavy rainfall, these materials often produce lahars, which are mud flows composed of volcanic debris and water that can travel long distances and cause significant damage. In summary, basaltic volcanoes tend to produce lava flows as their primary hazard, while andesitic volcanoes are more likely to produce explosive eruptions, ash, pyroclastic flows, and lahars. Another hazard is landslides. These occur when slopes become unstable and rocks, soil, or debris slide downhill. Landslides can be triggered by heavy rain, earthquakes, or other factors. They can be dangerous to people and infrastructure downhill and could cause subsidence in the area. The next hazard is tsunamis. These are giant waves that are secondary hazards, usually triggered by earthquakes or volcanic eruptions under the ocean. They can cause widespread damage to coastal areas, flooding homes and infrastructure, and can cause loss of life. It is important for people in areas that are prone to geological hazards to be prepared, with emergency plans and supplies on hand. Scientists also study geological hazards to better understand their causes and potential impacts, and to develop early warning systems that can help save lives. Geological hazards pose a risk to life and property, and the level of risk is associated with several factors. Population density is one of the most critical factors. Areas with a high population density are more vulnerable to the effects of a geological hazard. For example, an earthquake that strikes a densely populated area is likely to cause more casualties and property damage than one that occurs in a sparsely populated region. Technology and building standards also play a role in the level of risk posed by a geological hazard. Buildings that are designed to withstand seismic activity are less likely to collapse during an earthquake. Areas with better building codes and infrastructure are also more likely to recover quickly from a geological hazard. Development factors such as economic situation, education and communication also play a role. For example, areas with higher levels of poverty may lack the resources and infrastructure necessary to prepare for and respond to a geological hazard. In contrast, areas with better education and communication systems may be better equipped to understand the risks of geological hazards and take steps to reduce their impact. Hazard prediction is an important aspect of mitigating the impact of geological events on human life and property. However, predicting geological hazards with a high level of accuracy is challenging because the processes that lead to these hazards are often complex and influenced by a range of factors. Additionally, data and monitoring tools are not always available or sufficient to provide accurate predictions. For example, earthquakes can't be predicted as they occur due to the movement of tectonic plates, which are deep beneath the Earth's surface. Seismologists can use various methods to detect and monitor seismic activity, but predicting the precise timing and magnitude of an earthquake is still a significant challenge. At best, scientists can only calculate the probability that a significant earthquake will occur in a specific area within a certain number of years. Similarly, predicting volcanic eruptions, although more reliable, can be complex as it depends on the behaviour of the magma within the volcano. Seismologists, geologists, and volcanologists use a range of techniques to monitor volcanoes, including seismic activity, ground deformation, and gas emissions. However, even with these monitoring tools, predicting the timing and size of an eruption remains challenging. In summary, while scientists and researchers have made significant progress in hazard prediction, there are still limitations to the level of accuracy that can be achieved. Reducing the risk of geological hazards is crucial to minimise their impact on life and property. Some of the methods to reduce the risk of geological hazards include building design and regulation, hazard prediction, warning schemes, and evacuation. Building design and regulation can help to reduce the risk of geological hazards by ensuring that structures are built to withstand potential hazards, such as earthquakes or landslides. Building codes can specify requirements for construction materials and techniques that make structures more resilient to natural disasters. Prediction of geological hazards is also an essential tool to reduce risk. Scientists can use various methods to predict hazards, including monitoring patterns of seismic activity, ground deformation, groundwater changes, and gas emissions. For example, seismologists may look for seismic gaps, areas where an earthquake has not occurred for an extended period, in order to forecast where the next earthquake may occur. Warning schemes and evacuation plans are also vital to reduce the risk of geological hazards. By providing timely warnings to communities at risk, Individuals can take steps to protect themselves, evacuate if necessary, and reduce the impact of the hazard. Despite these methods, the level of accuracy of hazard prediction is limited. Geological hazards can be complex and unpredictable, making it difficult to forecast the exact timing and impact of an event. Therefore, it is essential to have emergency response plans in place and to educate communities on the potential hazards and ways to prepare for them.